In this video, we would like to discuss the value heaps, priority queues, and heap sort. The main idea in this video is to introduce how the data structure can help algorithm design. In the end of this video, our students would be able to understand two properties of value heap: elegant recursive structure and array-based representation. Two operations: adding an element and removing the highest or lowest priority element. Let's use one example to see why we need to learn priority queue, why we need to have this value heap. Let's say we got one task, and the customer asks us to use a data structure to implement a simulation for a job scheduling system. This job scheduling system is quite dynamic and it's hard to predict what will be the next job. Each job has one ID, arrival time, pre-processing time, and priority value. The job scheduling system is highly dynamic, where jobs will be scheduled based on priority value and arrival time. When the priority values are the same. Namely, the higher the priority value, the earlier the job being scheduled. First come, first scheduled if the priority values are the same. Here, example we give here, it is one table include 4 jobs. They may come at a different time, and they may have different processing time, priority value, and also vary. And then the first question, which one will be first scheduled? We see in the beginning, at the time 0, we have 2 jobs come. Job 1, job 2. Both come at the arrival time 0. And job 2 has highest priority 99. Job 1 has priority 2. So in this case, we are sure that job 2 will be scheduled first, right? That's true. And then the question 2 it is, if job 2 is scheduled, what will be the next scheduled? And we see that when the job 2 is scheduled, job 1 has to wait. And job 2 needs to take 20 units time to finish. At the same time, job 2 is scheduled, and job 3 and job 4 come one by one. And when the job 2 finishes, we need to pick up one job to execute it. And we see here, we have 3 jobs in the pool. If you have more new jobs coming, and then they will be stay in the pool. We want to pick up the one job which has the highest priority in the pool, and also if they have multiple jobs do have the same priority value, we use that job which has the earlier arrival time. So in this case, job 3 will be scheduled next time. And in this highly dynamic system, it's hard to sort all the elements very frequently. It will take more time. And also, since in this dynamic system, it's really hard to predict what will be the next one. And they may need to stay in the pool, and they have higher priority. You have the dynamic adjust when the elements in the pool in the sorted list. So we cannot frequently permute the odd elements in that pool in that list, and sort that, find the smallest or highest priority. So this reason the data structure value heap can really help. And the value heap is a complete value tree where each element is greater than or equal to both of its children. Value heap satisfy different properties. First, tree structure. Second, binary tree. And third, should be complete binary tree. The first odd element is greater than or equal to both of the children if there is a maximum heap. And the minimum heap, the only one thing is different it is every element, each element is less than or equal to both of the children. It's the smallest one in the root. And the max heap, which is the largest one in the loop. In this lecture, we use maximum heap. In one of the assignments, we use minimum heap. First, let's take a look at binary tree. Binary tree is a tree data structure in which each node has at most two children, which are referred to as the left child and the right child. And give this example, we say the first one, that is true. It is a tree, it is a binary tree. Second one, true. Third one, false. All these first four, they are true. The fifth one, that is not a tree structure because it includes a cycle. Because it includes from this node to this node, they could have multiple paths, right? And the last one also is not a binary tree because one of the nodes, they do have degree 3. That is what we do not like for binary tree. Complete binary tree is a binary tree satisfying the completeness property, and which corresponds to every level except possibly the last one is completely filled. All the leaf nodes in the last level are presented from left to right. It corresponds to if they have edge, if the edge is the height, then edge minus 2 totally full tree structure, right? And totally full tree structure. And also from the level 1 through, if this is edge, right? This is the from 0 through edge minus 1. In this part, there should be complete tree structure, right? And in the last one, the nodes came from the left to right. And also the edge 2 level from 0 to edge 2 level, in that case, every nodes do have 2 children. Okay, so take a look at this example. You can see the first 2 are complete binary tree, right? But the third one is not, because in these nodes, we're supposed to fill in these nodes and these nodes first, right? Then we can fill the next level. So this is not complete. Take a look at this one. This is also not complete because in these nodes, we miss left child, right? Doesn't matter how do you arrange that. This node should be totally complete, fill the children. Then you can fill the next children. Completeness, which is good structure and shape and property of a complete binary tree. Completeness property provides good structure and shape, right? And also the interesting thing it is this completeness following the recursive definition. In a complete binary tree, any subtree is also complete binary tree. A subtree of a tree T consists of a node in T and all its descendants in T. Any subtree has the completeness property. If this is a binary, it is the complete binary tree, then in such case, all the subtree, it is also complete binary tree. Right? For example, in the listed root, and this is a subtree of the 2 children of the root, which is also complete. The reason it is this definition requires we need to fill all the previous level and in the last level from the left to the right. In that case, any subtree included in this tree, they will never break these rules. And you can see even for next level, right? It's complete this property. And also in this binary heap, in the heap structure, it also satisfies ordering property. Corresponding to the truth for every node in the tree, the value stored in that node is greater than or equal to the value in each of its children. And for example here, 65, it is the root nodes. These root nodes should be the largest guy in the whole tree. And the 27 is the biggest guy of this subtree. We really don't care about these 27, if there are two nodes, they do not have a direct parent-child relationship. We really don't care about which one is bigger. We always care about it is the largest guy in the root or the smallest guy in the root. And also this ordering property also satisfies this recursive definition. An early subtree in a heap is also a heap, satisfying completeness property and ordering property. For example, 65 is the root, and its two subtree also is a heap structure, satisfying completeness property and ordering property, right? We said every node in the tree or subtree should be the largest guy or smallest guy. If it's a maximum heap, it's the largest guy. If it's minimum heap, and the root in the early tree or subtree should be smallest one. And we'll go to the next level, you will find out the subtree in the next level also is a heap. This is recursive definition, and can give you this 6 tree structure. Which of the trees can be represented as a heap? In that case, we have to check is completed. First, it's a balance tree or not. Second, is complete balance tree or not, right? In this case, this is not good because before you fill in the next level, you need to make sure all the previous level should be complete. And in this case, it seems is complete. This is seems complete. This is complete. So this one possibly, right? This is not complete because you need to fill it here, then you fill the last one, right? And also same thing here, you need to fill here. And then after you check the complete property, we have to check order property. We say this is wrong, right? Because no, in the root or it may be either the largest guy or the smallest guy, right? And take a look at number 2 and the option 2. And in that case, you check each loss and check these loss as the root for the subtree rooted by these loads to see if this guy is the highest guy. If this is in this subtree, it's okay. In this subtree, it's okay. In this subtree, it's okay. In this one, it's okay. So definitely 2 is correct. Let's check for 3. 3 we already checked is satisfied with completeness property. But for all the property, we check this one. No, it's not good. The 16 should be here. This part is okay. This part is okay. But this is wrong. So the correct answer is option 2. And completeness property determines the efficiency of array-based representation. Array-based representation easily maintains the completeness property when performing the insertion or maximum node remove operation. Array-based representation easily maintains the completeness property. Nodes are placed from top to bottom and left to right. Edges linking adjacent nodes are represented by implicit link, the relation of array index of 2 elements. So when we have to represent the heaps in array data structure, and we consider this complete property, we place each node from the top to the bottom. In each level, we place each node from the left to right. So the 65 should be here, and here we're starting from, in this array, we're starting from index 1. We will explain to you why we use index 1 as the starting point. And then we check each level by level, in each level, left to right. And the interesting thing it is, we use this order traversal to list each nodes and put in array, and the index relationship give us the the index relationship also show this parent-child relationship, right? Can you see that? And we see for load at the index I, its left child is at 2 times I, and its right child is 2I plus 1. And when the index starts from 1 for the presentation. So we start from 1 only because we this is easy for calculation. If you start from 0, you have to make sure this is 2 times I plus 1. And the right part to go to the 2 times I plus 2. It's just not so obvious. And also, the for load at the index I is left child, this one where it present, right? And also give this load, you can specify what could be the parent loads. For load at the index of I, and it left child 2I, right child 2I plus 1, parent load it is floor of I divided by 2. Give n node, the tree height it is log n. Since the binary we use log base 2n, the height of a load is the number of edges on the longest parts between that load and the leaf. The height of a tree is the height of the root loads. The depth of a load is the number of edges from the tree's root load to the load. And they also have some interesting properties. For example, given an n-node tree, the tree height is log n. The leaf nodes are present at the index of n divided by 2 plus 1 through n. Long leaf nodes are present at the index 1 through n divided by 2. And take a look at this example. We have 4 arrays. We want to check which array could be represented as a heap. In this case, we would like you to draw the binary heap, complete the binary heap, and the binary heap by using this array. For example, we see the elements at the first position should be the root, right? And the next one should be left child, and this should be right child, and we need to go to the 13 and 10. Right? Level by level, we have to show this relationship is A is 14. In this case, we check it's complete or not. It is satisfying the ordering property or not. Definitely it is not, right? Because this is the ordering property, it's not satisfying. 13 should be in the root of this subtree. And take a look at this one. Sometimes you can use this way if you think this is obvious for you. Right? And usually it will be better you draw that. And in this case, this is good. And take a look at this one. This is the left child and right child. And this is the left child, right child. In this case also, it does not satisfy the ordering property. And take a look at this one. Right? In this case, also not good. And they have different operations, and the most important that we have 3 operations we care about. Add new elements, add the given element to the heap, remove the maximum element in the heap, find the maximum. Find the maximum, we just need to return the reference to the maximum element in the heap. Let's take a look the elegant solution of adding element. Add element method, add a given element to the appropriate location in the heap, maintaining both the completeness property and ordering property of the heap. And for example here, we already have a binary heap. Now I want to add the 55 in the binary tree, in the binary heap, right? We see the first, every time when you insert or remove, we need to make sure the what the remaining tree still is the binary heap. So it satisfies complete property and order property. And let's say first let's make a complete property, and we have to insert 55 in the end of the list, right? Because it traverse in the list, the order based traversal. 55 should be the last guy. And then once you put 55 in the last guy, then the order property is not satisfied anymore, right? Because this subtree should be Bell heap. It's not. 55 is greater than 19. And such that we consider swap it with the root in the subtree and check with the upper level and swap it if the relationship is not satisfying and continue to check until the both property has been satisfied, right? Appending the new element, compare and swap the new element with its parent node if you need. Continuous process up the tree till the order property is maintained, and we call this procedure as bubble up. How long to bubble up a leaf node to the root, and which is depending on the height of the tree and depending on the number of edges in the longest parts. It corresponding to the height of the leaf nodes, right? The leaf nodes in the last level. And such that definitely since it's a barrel heap, it's barrel tree, it have a log n the height, right? So it means this runtime is all log n. And here we give you an example. We want to show what is the barrel heap for adding each element. So we add the 34 in array, we add the 45, it's not good, we swap it, and we check 3, and we check 87, we swap it until this procedure repeat until the root nodes is okay with the two properties. We add 65, we swap, and we add 32, we swap, and then we insert 12. So this is a heapify add, and we use iteration to do that. So the first statement, which get the last load. The second one, the while loop bubble up the new load until the order property it is okay. So this is the while loop, do that. And compared to the return negative 1, compared to return negative 1, if the load at the next is greater than its parent loads at the next divided by 2. And we have max heap in the package we put in the Google Drive, and you can download from here. Also, you can download from the canvas. These two statements in iteration move the parent load down. And finding the maximum is easy because you just need to retrieve the first element in the array. Definitely, it takes a constant runtime. To remove maximum, so in that case, it is we have to remove the root nodes. And we also need to keep the complete property and keep the order property. Once you remove the 65, in such case, the nodes at the index 0, index 1 become empty. It's not good for array data structure. It's not complete now, and such that we have considered to make completeness. One of the idea, which it is the move the last elements to the root position. In that case, a field gap. And then if the order property is not satisfying, then we think down with new nodes to specific compare these new nodes with the left child and right child, pick up the maximal guy and think down these new nodes. And for the same procedure, check the order property in the subtree rooted by these new nodes. And then for the same thing, same procedure, think it down until this subtree is satisfied, right? And such that every subtree is barrel heap, this is really barrel heap. And for this remove maximum operation, and consider this is a barrel heap, and the worst case, it needs to swap with the child nodes at a different level, and such that it take all log n runtime. And this is for exercise, and also in the quiz question. If we have to remove 87, then in that case we swap the last guy with put the last guy to the root position. We think down, right? And this is the code. We also have the packaging in the canvas and also in the Google Drive. and you can download from here. The while loop. So this is we also use the iterative approach to implement that. And in these statements, it will think down the new root, right? Pick up new root based on the index calculation. And the priority queue in which has wide applications, and it can store a collection of elements with associated priority, supports adding an element and retrieved element with the highest priority. In a priority queue, each element has a priority. An element with higher priority is served before element with lower priority. Tails are broken with standard first in, first out rule as with normal queue, right? And we have one specific project which implement this priority queue binary heap in the discrete event simulation. You can download this maximum heap from this Google Drive, update the maximum heap implementation to support the minimum heap. Create a birthday reminder system if you want, and also can use the barrel heap. Can we use the following data structure instead, which would be time complexity for each operation: an order array, an order linked list, order linked list. So for this one, you can think about that. And that's all for this video. Thank you for listening.